Alright, this is the second lecture in control volume. So let's take a look at a case that would deal with all the particulars involved here. Let's say we had a pipe that came in and it had an exit coming across here. It also had an exit that was back at a certain angle here. And the pipe went on, of course. But we're just going to look at this section of the pipe. Somewhere, somebody had to put some sort of bolt here to hold it. So I'm going to draw this particular setup right there. And now I'm going to start looking at the control volume. And we need to know some angles, so let's just say this is theta, and here's our normals coming out. Okay, so over here we're going to say this angle is alpha. So I'll start labeling these N2, N1, here's N3. Here's my velocities. I'll have V1. I'll say here's V2. Here's V3. Now what I'm going to do is I'm going to go ahead and create two copies of this. Here is my two copies. What I'm going to do is on the left hand side I am going to eliminate all of the velocities and inlets here, and I'm going to put my pressures on here. This will be P1A1, this will be P2A2, and this will be P3A3. And I'll go ahead and put my Fx and my Fy. Now my coordinates are going to be X and Y here. Now I better put my theta here. Here's my alpha. Okay, so I've got my drawing. The only thing I don't have is I don't have my body force, so I'll put my weight of my fluids here. Now again, we have to pay particular attention to what each one of these are. My F of X and F of Y is a force that is put on the surface through the steel. So these forces go into the steel, and through the steel they are basically equal and opposite to the forces that are as a result of the pressure inside the object. Here's what I mean. If you go in here and you look at the steel jacket, okay, so here's your two objects here. Here's your F of X and here's your F of Y. Now this is the actual jacket here. So this is the steel. So all this is the steel. There are forces that are put on this steel. Okay, since it's a steel, I don't need those here. Okay. In any case, so here, let me do it this way. So this is the steel jacket. The green is steel, or some type of hard, like a plastic or something. And the black line denotes the delineation between the water here and the outer jacket. Now let's see. Here I'm going to draw like a pressure diagram. Okay, so here is the pressure on this surface. And of course there is some along in here. And it could be a vacuum at some point. I mean, I could actually have, say there's a vacuum right here for some weird reason. There could be a small region right here of negative pressure and be pulling out on it. Say we had one here too. So here's a pressure diagram in which there's a small vacuum here. Anyway, so essentially this diagram, if you took it and copied it straight over, it would copy straight over to here. And as a result, you'd have an equal and opposite effect. So I don't know if I can draw this very well, but here you would have the force of the steel on the water. Here, force, I'll say pressure. And here's the pressure diagram of the water on the steel. Now you notice it's equal and opposite, which that's what it should be. Now, if you were to sum up all of these, you would get these forces right here. So these, in fact, this F of X and this F of Y is as a result of the jacket put on the outside of this water flow. So from that perspective, I can delete all this now that we have some understanding here, hopefully. And let's go to solving our problem. Sum of the forces is equal to change in time over the control volume, rho v d volume, plus integration around the whole and controlled surface is rho v, then a v dot n, and d area. Now, again, to reiterate, this is a scalar, and this term over here, I'll highlight in yellow the terms that deal with direction. So, let's go on now and figure up the x component. Now the beauty of this is I can change things on the fly. So let's say I wanted to find f of x. Then, as we talked about before, I'd change this to f of x. Now for some reason my t moved, but that doesn't matter. And now I'm looking at the vx here. Okay, so here's what we're looking at. We're looking at the x component. Now, technically, there should be an equal across here. So we look on this diagram to find this one. We look on this diagram to find that one. So if we look at our components, what we'll see, and we'll have to be really careful, I'll start with the f of x because it's already listed right here. So maybe I better change this to something like r of x in order not to confuse the f of x, sum of the forces in the x direction. So I'm going to call it r of x. Then I'm going to pick this one, P1A1. It's all in the x direction. This one is minus P2A2. Now, if you looked at this, and I'll slip in here and sort of try to sneak this in here. Here's your theta. So we're interested in this component of it right along in here. So what we end up with is cosine of theta. And now we need to deal with the component down here. It's going in the positive. The component there is going in the positive P3A3. Now again, we'll slip in here. Wait a minute. Slip in here real small like. And we're looking for this component where this is alpha. So we end up with cosine of alpha. And I think that's all we end up with. We end up with the force over the first surface, second, and the third surface. All the other surfaces, the black lines here, the surface force got translated into those reaction forces, like we talked about a second ago. Now we're dealing with the right-hand side. We're going to again restrict ourselves to the conditions in which these don't change over the volume. You could take them out several times. The volume itself doesn't change. So we're only looking at the surface conditions right here. Now we've got to pay really close attention to things. Okay, let's start with the first surface, rho, and I'm just going to subscript everything. V1x, V1, and these two went together to give us a minus here. Minus, and I'll put the parentheses noting that you're going to multiply that. Since these two are in opposite directions, then the cosine of the angle between them is 180, and therefore it becomes minus. And then I've got my area 1. Well, let's go to 2. Here's 2. Now we have to be really careful here. Rho 2 doesn't do anything. What is V2x? Well, we'll address that in a moment. But let's address the dot product. It becomes a plus V2 and then A2. And then finally, I get rho 3. What's the velocity? 3, the x component. I'm going to hang on to that, and then I'm going to be looking at, okay, the V3 and the N3, same direction. Now, let's be real careful about this, and what I'm going to do is copy this picture down and take a close look at it. So I copied that picture down real quick, and now I'm going to be looking at what is V1, the x component, V2, the x component, and V3, the x component. Because as you can see, buried in here, I have those terms right here, I have that term right here, and I have that term right here. And it's very important that I break these into their proper components. Now V2, the x component is just V1, the x component is just V1. Now V2 is not that way. So let's draw it over here to the side. And here's my V2, and there's my theta. So of course I need V2 to reference it, but if the theta were 0, it would basically be V2. It would be basically in this direction, but since it's not, I need the cosine of that angle. Now, the x component in the 3, now we have to be really careful. It's going in that direction. So here's what I mean. If you just broke V3 out and broke it into its components, V3x, and then there's V3y, and of course here's your alpha. This component, okay, remember our coordinates were like this. This component is in the opposite direction. It is a minus V3, and then you've got a similar setup there, cosine alpha. Now, let's copy this equation from up here down with the values stuck in it, and you'll see what we get. Now, here's what we have. Let's roam up a little bit. And what we're going to do is we're going to notice that first I didn't do anything but copy that equation down. And I copied these as well, although I want to work on these components. I want to insert the proper values for them from this little area right here. So if I go do that, I don't really have to do that much to the first one. I can slip in here and just write V1. Now over here I've got to do some moving around. So what I'm going to do is I'm going to basically take my values. I'm going to remove some things and whoop. I'm going to put right about in here the value there. Now what I mean by that is I'm going to take and insert that right here, and then I'll take this term, stick it back next to it. Whoop. Up. So there's that term, whereby I inserted this from right here. Now I've got to insert this one. Now what I'll do there is I'll insert that one by hand, so to speak, because it may take a little bit more to do that. So I'll say row 3, but what I have is I have a minus sign getting carried down, minus row 3 V3 cosine of alpha times another V3 times A3. So that takes care of all these terms. And now the question is, what would you know and what would you not know? I mean, first, you would know the pressures, areas, the angles. You can pretty much assume the densities are the constant throughout. So you know the angles, the velocities. Anything you didn't know you could find through continuity. And the only thing you wouldn't know is the reaction force. So I can take a moment and put numbers on this to give you some indication of how you would do this. Or I could generate another problem set off of this. And take off on this. But the key I wanted to get here was the delicate nature of each of these terms. For example, I wanted to pay close attention to this term and the fact that it was a component based, and close attention to the pressure terms and how they were represented on the drawing. And then we spent some time on these terms. And we broke them down, redid the drawing and broke it down component-wise. And then we ended up with the final equation. Now, yes, it would take a minute to put the numbers in here if we were given them. But instead of working on this problem, I'm going to come up with a new problem that looks very similar on the next video. So I hope I've covered everything. There's one more aspect, and I guess we'll go ahead and cover that here, and then look at it on one of the other videos as far as a numerical problem. So let's take a look at a completely different type of problem here. Here's what we've got. We have a gate, say, that may have broken and water came off, and so here's a river. This is concrete, say, and water came off and it looks kind of like this. And we know all the conditions here, so let's take, for instance, that this has a uniform velocity field of 5 feet per second. We're just going to start doing numbers here. Or I might want to change this a little bit, have the move the thing out in this particular direction. Let me redo this entire problem here. Since this is a non-numerical lecture, let's just set them up like this. Let's say you had a sluice gate and it came under, and it had a particular height down here, had a height up here, had a velocity coming out down here. I'll call this V1. I'll tell you what I'll do. I'll call each of these a little bit different. Height 1, height 2, velocity 2. Now, this is the ground, and so it has a hydrostatic pressure associated with it. And so let me set this up in the same sense that we talked about before here. We'll copy it, and we'll move over here, paste it. On the right side, we are worried about the velocities. On the left side, we are going to be mostly interested in the pressures. Now, let's take a look at our pressure diagram. Our pressure diagram is hydrostatic, meaning that it looks like this. There, in fact, lies the difference. Okay, some of the force is in the x direction, and we're just going to work off of a steady case. The area. Now, you could break this down to a summation over the control surfaces of rho Vx, V dot N times area, and sometimes some textbooks do this. Now, if you looked on the left end, you would see, okay, now, yes, I have an Fx here. I have a reaction force here. However, I could go in here and take that off and say, well, here's the water surface, but behind that there was some other surface. So there was some distribution here. So let's say there was a pressure distribution here. Well, the sluice gate that I pulled away had an equal and opposite pressure distribution. So these two should be the same, and as a result there's a reaction X here. So I would contend that this distribution matches that value, and this distribution matches that distribution, so I can just simply write minus reaction X, then I'll write plus gamma H1 bar A1 for that. Now remember, our gates, if we had a gate sitting somewhere, gamma H bar A was the actual force. Now I don't care where it's located in this particular case. It's a hydrostatic force. H bar is nothing, or H1 bar is nothing more than H1 divided by 2, but we'll talk about that in a second. Then I'm looking down here, I have this minus, so this one goes right here, gamma H2 bar A2, and that's all the forces I have. Now I can go in here and say rho. Well, Vx, the V1x, and then I have the normal. So I have a normal in this direction, have a normal in that direction. So I have a minus V1, A1, plus rho V2x plus V2 because the dot product. And one final term, gamma H1A over 2 minus gamma H2A over 2. Why did this come about? Well, here's why. Here is H1 bar. It's equal to H1 over 2. And the same thing down here. So this term is in fact that. And H bar 2 is in fact that. And I failed to put my subscripts there. But I'll complete this out. And since this term is nothing more than V1 squared A1 plus rho V2 squared A2. And that's it. Now you can go in and substitute in the values that you know, but we'll do that in the next lecture. So those are the two type problems. The type that have a hydrostatic force right here. So here's your hydrostatic distribution. And those that have pipes that are turned off at funny angles and going backwards and things. So these are the two most difficult problems, and these universally cover most everything that you need to know. There is one other type of problem that I will get to at a later time. And we'll go on from there and call this lecture done as well.